Hey everyone, in this video I'll be going over the derivation of the momentum equation, which is one of the three conservation equations we'll need for our CFD simulations. The first one being the conservation of mass, this one conservation of momentum, and the next one I'll do is the conservation of energy. So the conservation of momentum comes from Newton's second law, which is written up here. So it states that the sum of the forces is equal to the time rate of change of momentum. And this only works in an inertial frame. The time rate of change of momentum is this time derivative of momentum being the mass times the velocity. For our case, we're going to be looking at the derivation using a moving fluid element, in which case the mass is going to be fixed. So what we can do is we can take the mass out of the time derivative, and the time rate of change of velocity is just the acceleration. So the form that you probably remember or probably know the of Newton's second law is the F is equal to ma. So now let's just look at, so there's two sides to this equation. There's the force side and there's the mass times acceleration side. So we're going to save the mass times acceleration side for later, so forget about that side. We're just going to look at the forces now. So there are two kinds of forces that this fluid element can experience. There's something called surface forces, and then there's body forces. And there's multiple forces within those two sections of forces. So in terms of body forces, they act on the whole fluid element. So you can see there's three listed here. The first one's gravity. So these body forces act at a distance. So gravity acts at a distance. It's not like it's physically touching you and pulling you down to Earth. Gravity acts at a distance. We have electrical forces can act at a distance, and magnetic forces can act at a distance, which you see if you just have a compass or you have two magnets that you're holding, in both your hands, and they're both pointing towards each other, but they're not actually touching. So those are called body forces. And then we have something called surface forces, and there are three types of surface forces. The first one is going to be pressure, and then which acts normal to surfaces, and then you have the shear. Well, okay, so the other two, there's shear stress and there's normal stress. So there's stresses, so there's pressure and then there's shear stresses. In this case, we break up these stresses into shear and normal stresses, which you'll see why later. The shear stress is really based on the time rate of change of the shearing deformation of a fluid element, and the normal stress kind of looks like pressure because it acts normal to a surface, but it's based on the time rate of change of volume. And both of these stresses, shear stress and normal stress, both depend on the velocity gradient. Okay, so looking at the body force first, we're going to move up here. I'm going to say that we're only going to look in the x direction for this entire derivation, and we're going to get the x momentum equation, and then you'll see why we only do it for one, because they're pretty much the same for the y and the z directions. So I'm going to call this F sub x is the body force in the x direction per unit mass. And we know that the mass is just the density of the fluid times the volume of the fluid element. Because the units cancel, we have kilograms per meter cubed times the volume being meter cubed. So the body force ends up being, we're going to call it F sub body, is going to end up being in newtons, because the F of x is going to be newtons per mass, so it's going to be newtons per kilogram, and that'll cancel out with the mass. Okay, so that's the body force. We don't need to do anything more with the body force because it's a general. You can always split it up into, like I said, like the gravity, electrical, magnetic, but we just leave it as a body force. Now we're going to go to the surface forces because these are more interesting. So I drew the picture over here. It might be a little hard to see. So what I want to go through first is the nomenclature I use for the stresses. Pressure is fairly simple. It's just going to be denoted as P. And pressure always acts normal to the surfaces, and it's always pushing in, or directed into the element. Okay, so the nomenclature for the tau is that if you look at this one up here, these green ones, I color-coded them for which direction or which face they're on. So the green ones are on the top and the bottom face of this. The blue is on the front and the back, and then the red ones are on the right and the left. So the shear stresses are the green and the blue, because they're kind of pulling on the surface. And then the red forces, or the red stresses, are the normal stresses because they're normal to the surface. So the tau sub yx, in this case, It's acting on the top surface, so it's acting on it's the shear stress on the y surface. So we call it the y surface because it's perpendicular to the y-axis. So like the front face is the z surface because it's perpendicular to the z-axis. So we have we have the top one again we're looking at. It's on the y surface in the x direction. So this is moving in the x direction. So similarly on this front face, we're on the z face, right? And it's moving in the x direction, so we're going to call it tau zx. Okay. And then for the normal stresses, since it's acting on the x face and it's also moving in the x direction, we call it tau xx. Okay, so that's the nomenclature. In terms of sign convention, we assume that the velocities are, if you look it up at the top corner there, you see my velocity kind of axis, where the velocities are increasing along the positive axes. So what that means is, as I move from the origin out in the x direction, my u velocity is increasing. And similarly for the y and the z. So as I move from the origin up in the y, that means my v velocity is increasing. As I move from the origin out in the z, that means my w velocity is increasing. So why do we care? If I'm looking at this top surface here, I know that my velocity is going to be increasing as I move away from the origin. So what it's saying is, so the reason that this is actually pointing to the right and the bottom was pointing to the left is that as I move up, my velocities are increasing, which means I'm going to have it pulling. I'm going to have this face is going to be pulled. It's going to be kind of just pulled out because the velocity right below, if you can think of it as like an infinitesimally kind of thin plane, the velocity right below it is slower than the velocity above it. So the velocity above it's kind of pulling the flow along. And similarly on the bottom, you can think of it as like we are literally right below the origin when we move to the bottom face. So the velocity when we go negative is going to be slower. So the one on top is faster, and this is slower. So it's going to be pulling it. In the opposite direction. And then in the same way for the normal stress, again the velocity in the x direction. So the u velocity in x direction is increasing the farther we go up to the other side. So what you have is this kind of wall where the velocity right on the left of the wall is slower than it is on the right of the wall. So it's kind of sucking this velocity that's higher on the other side of the wall is kind of sucking the wall or the face out that way. And then here, where if we go in the negative x direction, the velocity is a little bit slower. So we're going to have it pulling out. We're going to have pulling out similarly in the same way that I was talking about in this face. Okay, so we have these they're not canceling forces, but we have on the top and the bottom we have the y face in the x directions, and then on the front and back we have these complementary kind of forces. In the same way that I went through the fluid element, the moving fluid element for the continuity equation, you can see that we have this term in here that's the change. It's the change in the tau yx in the y direction times some distance, and that, if you want a more in-depth explanation as to why you add this term to each of the shear stresses, you can look at the continuity. I'll post the video in the comments or in the description, and you can see why you add that. But it's pretty much just it's a change over a certain distance that you have to add to it because it's changing within this fluid element. Okay, so now that we have all of these forces essentially on here, what we want to do is we want to get the surface force. So we have the body force, and we want the surface force now. So what you can do is, since we're only talking in the x direction, you can just sum everything up in the x direction, assuming that the positive, we're going to add everything that's in the positive x direction, we're going to subtract everything that's in the negative. So we're going to add this pressure, subtract that pressure. We're going to add this normal stress, we're going to subtract this normal stress. So I color-coded them again here. So we have the pressure. So this pressure, we're going to add this pressure, which is here. We're going to subtract this pressure, which is here. And then I just take out the dy dz because it's common to both of these terms. In the same way, we're going to add this one because it's in the positive direction, subtract off of this one because it's in the negative direction. I took out the dy dz. With the bottom and top surfaces, we're going to add the top one because it's acting in the positive, subtract the bottom one because it's in the negative, take out the dx dz. And then for the front and back faces, we have adding the bottom one, or sorry, not the bottom one, the front one, because it's positive, and subtracting off the back one because it's negative, and we take out the dx dy. Okay, so what we want to do then is add, so the force, we broke it up into surface and body. So we're going to, okay, I guess I need to, I'll cancel some terms out first actually. Okay, so in this case we have this pressure, if we distribute everything through, we have this pressure ends up canceling this pressure out. And then we have, in this term, we have this positive is canceled with this negative. And then we have in this one, you can see where I'm going with all these, we have this one canceling out this term here, and we have this term canceling out this term here. So what we have is all these partial differentials essentially. So what we have here is we have the dp dx, or dp dx dy dz. And I'm going to so I'm putting that into this equation here. We're left with the d tau xx dx dx dy dz, and then similarly for the other two. So what I did is I just took out, since dx dy dz is similar to all of these terms, I took it out over here. So what I'm left with is, from here, I have this negative dp dx dx, so that's right here, or dp dx when I took out the other ones. Here I have plus d tau xx dx here. From this one I have plus d tau yx dy from here. Then here I have plus d tau zx dz here. They all have the dx dy dz, and then we're going to add on, so that was all the surface forces, we're going to add on the body force here, and we have rho fx dx dy dz. So from this equation, we have the left side of Newton's second law. So what we need to do now is we need to get the right side. So what I'm going to do is I'm going to erase this up here, and I'm actually going to erase this too, and this as well. Okay. So I'm leaving this bottom equation so we can see that. Okay. So we know that the mass of the fluid element is equal to the density times the volume of the fluid element. Okay. So that takes care of the mass. The acceleration, we know that the acceleration, A, and we're going to call it just in the x direction now, is the time rate of change. It's the time rate of change of velocity, right? So it's du dx. But what du dx do we use? Since we're tracking a moving fluid element, we're actually going to have to use the total or substantial derivative that I talked about in my other video that I'll post a link in the description. So when we're talking about the time rate of change of velocity, it's actually the total time rate of change of velocity. So the acceleration in the x direction ends up being this, where normally you would have seen it as, just a du dt. So if it had been a fixed fluid element. So now we can put these two together. When we combine these two, we get rho du dt, and I'm using u because we're talking about the x direction. And then we have dx dy dz. So now if we combine this part for the mass times acceleration part with the left side, you can see that we'll get, this is the left side here, you can see that we will end up, and I'm going to take this on the left side, this on the right side. So we're actually going to have rho du dt dx dy dz is equal to this part here. So we have this negative, that's a partial, whoops, daisy. This is a partial differential, so we have dp dx plus d tau xx dx plus d tau yx dy plus d tau zx dz dx dy dz plus the body force, which also has dx dy dz. You can see where this is going. We can divide through by the dx dy dz term, like that. And then what we end up with as our final equation for the x momentum is rho du dt, and just bear with me because I'll just rewrite this really quickly. is equal to negative dp dx plus d tau x dx plus d tau y x dy plus d tau z x dz plus the body force. So that was the surface force, this is the body force now, rho fx. Okay, so this gives you the x momentum equation. This was derived using a moving fluid element, which means it's giving us the equation in non-conservation form, also in partial differential equation form. We can change this to conservation form using mathematical manipulation, but this just happens to be obtained using the moving fluid element, so it's in non-conservation form. Okay, so this is just the x equation. You can get the y and the z equation similarly to what we did just using the y or the z forces. It's going to be the same kind of equation here, except here you'll have a rho dv dt or a rho dw dt. Here you'll have dp dy or dp dz, and then here these are going to change from, this one would be like the tau xx would change to tau yy, because now we're talking about the y, or tau zz, and similarly these would change. So what you have there is you'd end up having these three equations for x, y, z, and the momentum, and those three equations are what is actually called, it's actually called the Navier-Stokes equations. So you've probably heard of the Navier-Stokes equations, and you'd think that it was, you know, the full continuity, momentum, and energy, but really the Navier-Stokes equations are only the momentum equations. But nowadays, you know, everybody calls the full set of equations the Navier-Stokes equations, so that's just a little tidbit. And I think that's all I want to talk about in terms of the momentum equation. And I guess the next video I'll do is the conservation of energy. So, thank you for watching, and stay tuned for the next video.